In section 3.4, we will learn a new approach to graphing quadratic functions. At this point, we know how to graph a quadratic function using transformations, but in some cases that is not always convenient. Let me scroll down to page 2 of our notes and show you the two forms that we're going to consider in this section. The first form, called Vertex Form, is a familiar form. That is, I can recognize that it's a quadratic function. It graphs as a parabola. It's been stretched by a factor of a. It's moved to the right by h units, and it has moved up by k units. When we see a parabola presented in this form, we can graph by transformation. However, if the parabola is given in a more general form, that is, all of the terms of the vertex form have been multiplied out and combined, then we can't look at that function and read the transformations. It's this type of function that we're going to learn how to graph in this section. But what these two forms have in common is their leading coefficient. That leading coefficient gives me important information about the properties of the parabola. So back to section 3.4.1, the properties of the parabola. If that leading coefficient A is positive, that is, a is greater than 0, then we can recognize the parabola opens up. So the purple parabola here would have a leading coefficient greater than 0, and the red parabola would have a leading coefficient greater than 0. However, if that leading coefficient A is less than 0, now think about that. You have learned that that represents a reflection across the x-axis. If I reflect a parabola across the x-axis, then it opens down. So if we have a negative leading coefficient, the parabola opens down. So looking at our blue parabola here, that has a leading coefficient that is negative or less than 0. Now, all of these parabolas have a very important point that we're going to recognize. This point is what we call the vertex of the parabola. It's where the parabola in this case goes from decreasing to increasing, and the same is true right here. Or in this case, the parabola changes from increasing to decreasing. So we can think of the vertex as a turning point for that parabola. Now, if the parabola opens up, then the vertex is a minimum point. And if the parabola opens down, then the vertex is a maximum point. That will be important when we study applications. So we can look at a function and determine the direction of opening and then predict if that function will have a maximum or a minimum. Notice all of these parabolas have a type of symmetry. If I construct a vertical line through the vertex, it's going to divide that parabola in two mirror images, two matching halves. This line is called the Axis of Symmetry. Every parabola is going to have one. It's simply a vertical line that passes through the vertex, and it functions as a mirror. So on either side of that axis of symmetry, we can find points that are mirror images of each other. And they exhibit the property that they are equidistant from that axis of symmetry. In addition to the vertex and the axis of symmetry, other points that we will be interested in calculating would be the x-intercepts. That's always a good point to know when you analyze a function. In the case of our purple parabola here, we have two x-intercepts, whereas in the case of the blue parabola, we only have one x-intercept. And notice the x-intercept in this case is the same as the vertex. We could describe that parabola as bouncing on the x-axis at that vertex or touching the x-axis and turning around. If we look at the red parabola, notice it has no x-intercepts. Every parabola can have a maximum of two x-intercepts. And as we usually study with the x-intercepts, we also consider y-intercepts. So in the case of this parabola, we have one y-intercept. If we look at the red parabola, even though I cannot see the y-intercept on the grid, we know that this parabola continues extending, and it will eventually come up and cross that y-axis somewhere up here. The same thing's true for this blue parabola. Even though I can't see the y-intercept, it will eventually cross that y-axis at some point. So all parabolas are going to have exactly one y-intercept. Previously, when we graphed by transformation, we started with a parent function, we observed the mathematical operations in the function and translated those into how to move the parabola in the coordinate plane. Our approach in this section will be after that parabola lands, where's the vertex, what are the x-intercepts, where's the y-intercept, and what's the equation for the axis of symmetry. So we're going to be solving for these properties without transformations. Now let's practice recognizing those properties. Example 1, identify the vertex, domain, range, whether A, remember that represents leading coefficient, is positive or negative, and draw and label the axis of symmetry. Circle the x-intercepts and the y-intercept. So let's start with the orientation of this parabola. The parabola opens up. Since the parabola opens up, we know that its leading coefficient is positive. So we can say since the parabola opens up, the leading coefficient is positive. Now, since it opens up, that indicates that our vertex is a minimum. So I'll just make a note of that. Vertex is a minimum point. As soon as we identify that vertex, we can also recognize the axis of symmetry. Remember, the axis of symmetry is a vertical line that passes right through that vertex. Generally, we draw it as a dashed line because it's not really part of the graph. It's only a reference line. But this is our axis of symmetry. Points on either side of the axis of symmetry at the same elevation are equidistant from that axis of symmetry. Looking at this parabola, we can also recognize it has two x-intercepts. So remember, an x-intercept is simply where the graph crosses the x-axis. So this guy has two x-intercepts. In addition, there is one y-intercept. I have a bad habit of writing over the points that I'm trying to recognize. So that red point there is our y-intercept. Now, observing this parabola as a whole, if we wanted to recognize the domain of every quadratic function is always negative infinity to infinity. The range, however, will be limited by the location of that vertex. So for the range, we're going to identify the lowest point, that is our minimum vertex, and observe its elevation or y value. Now the scales aren't labeled here, so we'll assume a unit of 1. So 1, 2, 3. Looks like our lowest y value here is -3, and we'll put that in brackets. And because the parabola continues extending up forever, the maximum value for our range is infinity. So that is the domain and range of our parabola. One more thing before we move on to the next section. We've considered two orientations of parabolas that open up or down. There are parabolas, by the way, that open to the left or to the right, and we even have parabolas called oblique parabolas that open on a slant. However, those parabolas do not pass the vertical line test. If I construct a vertical line in a proper way, let me do a better job on my slanted parabola here. I'll emphasize it a little more. If we construct a vertical line on our slanted parabola, we can also see that we can intersect it in more than one spot. So these are not functions. For that reason, we're only going to study those parabolas that open up or down because they do pass that vertical line test.